Welcome. This is Sleepy Alchemy. There's nowhere to be tonight. Right now, somewhere in Earth's mantle, a diamond is growing. It's been adding atoms to its surface for tens of millions of years. In that time, it has moved roughly the distance a human fingernail grows in a year. That's the pace of tonight. The ground beneath you is not what it appears to be. The ground beneath any point on Earth's surface is not a single solid mass. It is a layered arrangement of mineral grains, compressed together under forces accumulated over billions of years of geological activity. The uppermost portion of this structure, the crust, is composed primarily of silicate minerals. Silicates are compounds in which 4 oxygen atoms bond to a central silicon atom arranged in the shape of a 4-faced pyramid, a geometry crystallographers call a tetrahedron. That tetrahedral form, 4 faces, 4 vertices, 6 edges, every angle precisely determined by the electrostatic behavior of the participating atoms, represents, according to available data, one of the most structurally stable arrangements of naturally occurring inorganic matter on the surface of this planet. Before we go any further, there's something worth settling into. The information that follows was not gathered in haste. It was drawn from measurements, from diffractometers, spectrometers, drill cores, and decades of laboratory work. And nothing is being asked of you here. There is no test at the end of this narration. No retention is expected. The information can be received the way stone receives heat from the sun, gradually, at the surface, with no particular urgency about what's happening deeper down. The Earth's crust, as a material body, is roughly 30 to 50 kilometers thick beneath most continental interiors and considerably thinner beneath the ocean floor, sometimes less than 10 kilometers. Within that thickness, minerals and rock types are not distributed evenly. Differences in density, gradients in chemical composition, and the thermal history of each region all determine what exists where. A drill core extracted from continental crust passes through layers of granite and gneiss, through zones altered by ancient hydrothermal fluids, through sedimentary sequences recording shallow seas that existed hundreds of millions of years ago. Every centimeter of that core is a record of a distinct set of physical and chemical conditions, different from the centimeter above it, different from the one below. The minerals inside that core have no awareness that they are being studied. This is one of the most consistently calming aspects of the discipline of materials science. The objects of inquiry are entirely indifferent to observation. A quartz crystal growing inside a hydrothermal vein 3 kilometers below the surface at 300 degrees Celsius has no knowledge that humans will eventually extract it and measure oxygen isotope ratios in a cleanroom laboratory. It continues adding atoms to its faces at a rate determined solely by the temperature, pressure, and chemical saturation of the surrounding fluid. The measurement, when it finally does occur millions of years later, simply reads what the crystal recorded, unintentionally. Matter that operates this way, without intention, without narrative, in complete compliance with the non-negotiating laws of physics, is structurally restful. A feldspar crystal growing inside cooling granite does not choose its cleavage angle. That angle is the inevitable consequence of how aluminum and silicon atoms arranged themselves in the melt before the crystal solidified. The fracture, when it eventually comes, will follow the bond geometry laid down while the rock was still liquid. Nothing about that outcome was ever decided. It was geometrically unavoidable from the first moment the crystal began to form. This narration sustains that quality throughout. Things happen because atomic geometry permits them or demands them, and for no other reason. Granite, one of the most abundant rock types in the continental crust, is composed primarily of three minerals: quartz, feldspar, and mica. At a scale far smaller than the eye can resolve, each of these minerals maintains its own internal crystal lattice, a repeating three-dimensional framework of atoms bound in consistent geometric patterns. In quartz, silicon and oxygen atoms alternate in a continuously linked network of bonded tetrahedra, spiraling along an axis that crystallographers classify within the trigonal crystal system. That symmetry is not decorative. It is a direct expression of how those atoms pack most efficiently under the pressure and temperature conditions in which quartz typically forms. Basalt is quite unlike granite. It forms from magma that is relatively poor in silicon, cooling rapidly at or near the surface. That speed of cooling leaves very little time for large crystals to develop. The result is a fine-grained rock in which individual mineral grains measure only fractions of a millimeter, too small to distinguish without magnification. Examined under the polarized light of a petrographic microscope, the texture of basalt reveals a dense, interlocking mosaic of tiny crystals, each oriented at a slightly different angle from its neighbor. Quartz, as a mineral, belongs to the trigonal crystal system and carries the chemical formula silicon dioxide, SiO2. Every silicon atom in quartz is surrounded by 4 oxygen atoms. Every oxygen atom is shared between 2 silicon atoms. This unbroken sharing creates an internal framework so continuous that, under the right conditions, it can extend without interruption for several centimeters within a single crystal. The internal order of a well-formed quartz crystal is among the most geometrically regular structures produced by naturally occurring inorganic matter on Earth. Beneath the visible surface of a rock, at scales measured in nanometers, small voids exist, gaps between atomic planes, defects in the lattice, vacancies left behind by atoms displaced through earlier chemical reactions. These voids are not flaws in any engineering sense, they are structural features. Research in the fields of rock acoustics and seismic petrophysics indicates that these microscopic openings influence how sound energy propagates across rock. When compression waves pass through stone, a portion of that energy is absorbed and scattered within these atom-scale apertures. Stone, then, carries a measurable potential for damping vibration, not merely by virtue of its mass, but because of the geometry of its internal architecture. The physics of sound propagation through crystalline solids falls under a branch of condensed matter physics that describes vibrational energy passing through crystal lattices as quantized units called phonons. A phonon is not a particle in the conventional sense. It is a quantum of vibrational energy propagating through the ordered arrangement of atoms in a crystal. The wavelength and frequency of phonons determine how they scatter off lattice defects, grain boundaries, and the microscopic voids described earlier. Phonon scattering is the primary mechanism by which both thermal and acoustic energy attenuates within rock. A phonon traveling through a perfectly regular crystal lattice, no defects, no grain boundaries, no voids, would propagate with minimal scattering. Real rock, with its grain boundaries, fractures, fluid inclusions, and chemical heterogeneities, presents an extraordinarily complex scattering environment. Every encounter with every irregularity redirects a small portion of the phonon's energy, redistributing it across a broader range of frequencies and directions. The cumulative effect of billions of such scattering events per second is the gradual decay of acoustic energy passing through stone. When a tuning fork is pressed against a large granite outcrop, the vibration does not travel through the rock indefinitely. It is progressively absorbed into the thermal energy of the lattice over a distance that depends on the rock's composition, grain size, and degree of fracturing. Perceptually, this is what gives stone its distinctive acoustic character, not silence, but a particular kind of dampening that softens sharp sounds into something more diffuse. The boundaries between adjacent mineral grains within granite, the surfaces where one crystal ends and another begins, are called grain boundaries. These boundaries are zones of slight misalignment. The atoms at the edge of one crystal do not bond perfectly with the atoms at the edge of the neighboring crystal. This means grain boundaries tend to be chemically reactive zones, more susceptible to weathering than the crystal interiors themselves. Water moving through granite preferentially follows these boundaries. Feldspar, the most abundant mineral in the continental crust, shares the silicate framework of granite, but incorporates aluminum atoms alongside silicon within the tetrahedral network. Different varieties of feldspar also carry sodium, potassium, or calcium ions lodged into the cavities of the lattice. How these larger ions fit, or sometimes barely fit, into the crystal framework determines the angles of cleavage planes, the color, and the thermal behavior of each feldspar variety. Mica, the third major component of granite, belongs to a mineral group known as phyllosilicates, layered silicates. Rather than a three-dimensional network, mica builds its structure in flat, two-dimensional sheets. Silicate tetrahedra link into continuous planes, and those planes stack on top of one another, held together by relatively weak electrostatic forces between the layers. This is why mica can be split into thin, flexible, translucent sheets with very little force. The layers simply slide apart along those interlayer bonds. Basalt frequently contains a mineral called olivine, a magnesium iron silicate with the chemical formula MgFe2SiO4. Unlike quartz and feldspar, olivine contains no aluminum. Its crystal structure is classified as orthorhombic, 3 axes of unequal length, all meeting at right angles. Olivine is among the minerals to first crystallize when silicon-poor magma begins to cool, which makes it a reliable indicator of high-temperature magmatic processes. Its characteristic color, ranging from green to olive yellow, derives from the presence of iron ions within the crystal lattice. The silicon-oxygen bond, the SiO bond, is, according to available geochemical data, one of the mechanically strongest bonds present in common earth minerals. Its average bond length is approximately 1.62 angstroms. the energy required to break it is significantly greater than that required to break many other common mineral bonds. This bond strength is the primary reason silicate rocks resist mechanical breakdown so effectively. A quartz grain that has been tumbling along a riverbed for thousands of years survives that journey because its internal SiO bonds hold against every impact. Crystal cleavage, the tendency of a mineral to fracture along specific planes, is a direct expression of internal bond geometry. Where the lattice contains planes of relatively weaker bonds, the mineral tends to break more cleanly along those surfaces. Feldspar has two cleavage directions that intersect at angles close to 90 degrees in some varieties. Mica cleaves so perfectly along a single plane that the resulting surfaces appear smooth and reflective at macroscopic scale. Porosity in rock, the fraction of total volume occupied by open void space, varies considerably between rock types. Freshly solidified basalt can be very low in porosity, with grains locked tightly together. But basalt that cooled rapidly at the surface of a lava flow frequently preserves vesicles, spherical voids left behind by gas bubbles trapped as the lava solidified. These vesicles can later fill with secondary minerals precipitated from groundwater, producing what geologists call amygdals, rounded mineral masses sitting within a fine-grained basalt matrix. Quartz possesses a property most minerals lack: piezoelectricity. When mechanical stress is applied to a quartz crystal, when it is compressed, twisted, or bent, the displacement of silicon and oxygen ions within the lattice generates a measurable electric charge across the crystal's surface. Conversely, applying an electric field to a quartz crystal causes it to deform slightly. This coupling between mechanical stress and electrical response is a consequence of the crystal lacking a center of symmetry. This is not a chemical reaction. It is a purely structural, atom-scale phenomenon. The piezoelectric effect in quartz arises specifically because the crystal lacks a center of inversion symmetry, the geometric condition in which every atom in a unit cell has a corresponding atom in the identical position on the opposite side of a central point. When a crystal with inversion symmetry is deformed, the positive and negative charge centers within the unit cell move symmetrically, and the net electrical effect cancels out. The helical arrangement of silicon and oxygen atoms in quartz breaks that symmetry. Deformation displaces the charge centers unequally. The resulting charge separation across the crystal face, the piezoelectric voltage, is proportional to the applied stress. The relationship is linear and reversible. Doubling the stress doubles the voltage. Removing the stress removes the voltage. In laboratory and industrial applications, the precision of this relationship in natural quartz has become the standard for frequency control in oscillators, devices that, when cut at a specific orientation relative to the crystallographic axes, vibrate at a frequency determined by their physical dimensions and elastic constants. That frequency is stable to within parts per million over extended periods, a stability that traces directly back to the regular, defect-minimized geometry of the crystal lattice itself. Industrial quartz oscillators use crystals grown from laboratory solutions in high-temperature autoclaves, the same hydrothermal growth chemistry that forms natural quartz veins, accelerated and brought under control. According to petrological data, The size of crystals within an igneous rock is a reliable indicator of how rapidly that rock cooled from a melt. Slow cooling gives atoms more time to migrate through the melt and attach themselves to growing crystal surfaces, producing larger grains. Rapid cooling freezes the structure before large crystals can develop. Granite, with its visible mineral grains, cooled slowly, typically kilometers below the surface, insulated from rapid heat loss. Basalt, fine-grained and dense, cooled dramatically faster. Thin surface lava flows solidify their outer crust within hours to days, while thicker flows may take weeks or months to cool through entirely. Still a blink compared to the tens of thousands of years granite required. None of these first 13 details are in any hurry. They are simply part of the stone that has always been there, beneath the roads, beneath the fields, beneath the foundations of buildings. The world rests on this architecture, and this architecture has been sitting quietly in place for longer than most numbers can comfortably express. We continue through the video unhurriedly. Each detail arrives in its own time, the way a mineral grain settling slowly through a water column moves. Not quickly, not dramatically, just steadily downward until it comes to rest on a surface. Thermal conductivity, the rate at which a material transmits heat, differs meaningfully between granite and basalt. According to geophysical measurements, granite, with its interlocking mosaic of quartz, feldspar, and mica, conducts heat at roughly 2.5 to 3.5 watts per meter per Kelvin. Basalt tends to conduct somewhat less efficiently. These differences have consequences for how heat moving upward from Earth's interior travels through the crust over geological timescales, and they govern the surface temperature gradients measured in deep boreholes. Seismic energy generated by the movement of large rock masses travels through the crust as waves. Two principal wave types propagate through solid rock: compression waves, which push and pull rock particles along the direction of travel, and shear waves, which displace particles perpendicular to it. The speed of both wave types varies with the density and elastic properties of the minerals involved. Quartz-rich granite carries seismic waves at different velocities than olivine-rich basalt, and seismologists use these velocity differences to map the composition of rock layers that no drill has ever reached. Many minerals do not have a fixed composition. Instead, they form what chemists call solid solutions, continuous series of compounds in which one atom can substitute for another of similar size and charge within the crystal lattice. Plagioclase feldspar, for instance, extends without interruption from sodium-rich albite to calcium-rich anorthite. At any point along that series, sodium and calcium atoms substitute for one another within the crystal structure, without fundamentally altering the lattice geometry. The ratio of sodium to calcium depends on the temperature and chemical environment at the time of crystallization. As granite formed deep in the crust, brought progressively closer to the surface over millions of years by the erosion of the rock above it, it experiences a reduction in the confining pressure that once surrounded it. As that pressure decreases, the rock expands slightly. Under certain conditions, this expansion produces curved, sheet-like fractures roughly parallel to the surface in a process called exfoliation. Large granite outcrops in certain landscapes develop these curved sheets, which eventually separate from the main rock mass and slide or fall away. The color of minerals is often determined by trace amounts of transition metal ions within the crystal lattice. Iron, in particular, is responsible for a wide range of colors in silicate minerals. Feldspar, in its pure form, is typically white or colorless. Small amounts of iron introduce pink, red, or deep rose tones. Quartz, also colorless when chemically pure, becomes purple amethyst when trace amounts of iron are incorporated into specific lattice positions and subsequently exposed to natural radiation over geological time. As silicate rock approaches and eventually reaches melting temperatures through burial and the accumulation of geothermal heat, it transitions into silicate melt. The viscosity of that melt, its resistance to flow, is not a fixed property. It varies considerably with temperature, pressure, and chemical composition. Melts rich in silicon, of the kind that solidify into granite, are highly viscous. They flow slowly and resist deformation. Melts poor in silicon, of the kind that produce basalt, are far less viscous and can travel rapidly across a landscape once they reach the surface. The viscosity of a silicate melt, its resistance to flow under an applied stress, can vary by more than 10 orders of magnitude depending on composition and temperature. That is a range spanning from something close to water to something 10 billion times more resistant. Understanding that range requires looking at the structure of the melt itself, because silicate melts are not simple ionic liquids. At the molecular level, a silicate melt retains some degree of the structural organization of the solid mineral it came from. Silicon-oxygen tetrahedra persist within the melt, bonding and unbonding to the extent that temperature permits. In a silicon-rich melt, the kind that will eventually produce rhyolite or granite, the proportion of polymerized silicate network in the melt is high. Many tetrahedra remained linked to one another, forming chains, rings, and larger networks that persist even in the liquid state. The difficulty of moving these interconnected structural units past one another is, at the atomic level, the source of high viscosity. In a silicon-poor basaltic melt, fewer tetrahedra are linked, the network is more fragmented, and the melt flows far more freely. Temperature directly modifies this structural landscape. As temperature rises, thermal energy is sufficient to break more of the bridging oxygen bonds connecting tetrahedral units, reducing the average degree of polymerization and lowering viscosity. The relationship between temperature and viscosity in silicate melts is not linear. Viscosity drops dramatically over a relatively narrow temperature range as the network progressively breaks apart. At 1200 degrees Celsius, a basaltic melt typically has a viscosity in the range of tens to low hundreds of Pascal seconds, depending on its exact composition. A rhyolitic melt at the same temperature may be 1,000,000 times more viscous. The difference is entirely chemical. The same thermal energy is available to both, but there is far more silicate network structure to break down in the rhyolite. Dissolved water in a silicate melt lowers its viscosity by introducing hydroxyl groups that break bridging oxygen bonds, the same mechanism by which water weakens mineral lattices in the solid state. Even a fraction of a percent of dissolved water can reduce the viscosity of a rhyolitic melt by several orders of magnitude. This effect has significant consequences for how readily such melts can move and degas, and it is studied in volcanology as a factor in eruption dynamics. A single chemical compound can sometimes exist in more than one crystalline form, depending on the pressure and temperature at which it forms. This property is called polymorphism. Quartz silicon dioxide is perhaps the most familiar example. Under surface conditions, quartz is the stable form of SiO2, but at higher pressures, the same chemical composition reorganizes itself into a denser structure called coate, in which each silicon atom is surrounded by oxygen atoms in a somewhat more compact geometry. At still higher pressures, an even denser form called stishovite develops, in which silicon occurs in octahedral rather than tetrahedral coordination. Thermodynamically, quartz is the stable form at surface conditions, but coate and stishovite, once formed, are kinetically resistant to reverting. They require deliberate heating to convert back. This is why both minerals survive in meteorite impact craters for millions of years, preserved long after the extreme pressures that created them have vanished. The Mohs hardness scale ranks minerals from 1 to 10 according to their ability to scratch one another. Talc, with its loosely bonded layered structure, occupies the low end at 1. Diamond, a three-dimensional network of strong carbon-carbon bonds, sits at the top at 10. Quartz registers at 7, hard enough to scratch glass, not hard enough to scratch topaz. These hardness values correlate directly with the strength and geometry of the atomic bonds holding each mineral's lattice together. Rock stores thermal energy with a capacity defined by specific heat, the amount of energy required to raise 1 gram of a material by 1 degree Celsius. Most silicate rocks have specific heat values that fall between 700 and 900 joules per kilogram per Kelvin. Large masses of stone, cliffs, boulders, cave walls absorb solar heat through the day and release it slowly through the night, creating temperature gradients in their immediate surroundings that persist for hours after the heat source has withdrawn. In this sense, stone functions as a thermal reservoir, buffering the microenvironment around it. Some minerals emit visible light when exposed to ultraviolet radiation or stimulated by other energy sources under laboratory conditions. This property, called luminescence, is present in minerals including fluorite, calcite, and certain feldspars. In some cases, minerals that have spent millions of years absorbing radiation through their geological history release that stored energy gradually as light when heated in a laboratory setting. This phenomenon, known as thermoluminescence, has been used in scientific research to estimate how long ago certain sediments were last exposed to sunlight. Quartz fractures in a distinctive pattern known as conchoidal fracture, not along flat cleavage planes, but across smooth, curved surfaces that resemble the inside of a clamshell. This arises because the bonding in quartz is uniform across the lattice in all directions. There are no preferred planes of weakness along which it consistently breaks. Early human toolmakers working with flint and obsidian, materials that share this conchoidal fracture pattern, relied on precisely this property to produce sharp-edged cutting tools through carefully directed percussion. Basalt frequently carries particles of magnetite, an iron oxide mineral with the formula Fe3O4, distributed throughout its matrix. Magnetite carries a magnetic moment. It behaves like a small permanent magnet. When basalt solidifies from a melt, magnetic particles align with Earth's ambient magnetic field at that moment. This alignment is preserved as the rock cools below the Curie temperature, the point at which magnetic minerals lock their orientations permanently in place. Ocean floor basalt retains this frozen magnetic record, and that record has given geophysicists a detailed history of how Earth's magnetic field has changed over time. These 25 details belong entirely to the surface and near-surface world, to rock that can, in some cases, be touched. What comes next concerns conditions no human instrument has directly sampled: the deep interior, where pressure exceeds what most laboratory apparatus can sustain, and where carbon becomes something the surface would not recognize. Kilometers below the surface, pressure becomes the dominant variable governing how matter behaves. Not temperature alone, nor chemistry alone. Pressure, the accumulated weight of kilometers of rock pressing inward from every direction simultaneously. Under these conditions, atomic structures that are perfectly stable at the surface become metastable, then unstable, and eventually transform into denser, more compact forms that the surface world would never produce on its own. There is no need to rush toward these depths. These processes took hundreds of millions of years. They can be described slowly. Carbon is an element that forms 4 chemical bonds simultaneously, a property that gives it the capacity to build molecular architectures of exceptional variety. In diamond, every carbon atom is bonded to exactly 4 neighboring carbon atoms, each bond directed toward the corner of a regular tetrahedron. The result is a continuous 3-dimensional lattice of carbon-carbon bonds extending without interruption in every direction. No atom in the diamond lattice occupies a surface position unless the crystal itself ends. The crystal structure of diamond belongs to the cubic crystal system, the most symmetrical of the 7 crystal systems. Within diamond's cubic unit cell, carbon atoms occupy positions that maintain the same bond length, approximately 1.54 angstroms, and the same bond angle, 109.5 degrees, throughout the entire structure. According to materials science data, this uniformity is directly responsible for diamond's exceptional hardness. Every direction through the crystal encounters the same dense network of strong bonds. Graphite, the other common form of pure carbon at surface pressures, has an entirely different structure: flat sheets of carbon atoms arranged in hexagonal rings, stacked loosely on top of one another. The carbon-carbon bonds within each sheet are strong. The bonding between sheets is weak. This is why graphite is soft enough to leave a mark on paper. According to current geochemical understanding, converting graphite or other carbonaceous material into diamond requires both high pressure, generally above 4.5 gigapascals, and elevated temperature, typically between 1,000 and 1,300 degrees Celsius. These conditions correspond to depths exceeding roughly 150 kilometers within Earth's mantle. According to available isotopic data, The rate at which diamond crystals grow in nature is extraordinarily slow. Growth rates estimated from inclusions within natural diamonds suggest that individual crystals may have grown at fractions of a millimeter per million years under natural mantle conditions. A single pea-sized diamond may represent tens of millions of years of atom-by-atom accretion, one layer of carbon atoms at a time, settling into the crystal lattice at whatever pressure and temperature permit. Diamond holds a record in materials science. It possesses the highest thermal conductivity of any naturally occurring material, ranging from approximately 900 to 2,320 watts per meter per Kelvin, depending on purity and isotopic composition. This is a consequence of its crystal structure. Heat in solids travels primarily through vibrations propagating across the lattice, phonons in the language of condensed matter physics. Diamond's rigid, uniform lattice allows these vibrations to propagate with minimal scattering, enabling exceptionally efficient heat transfer. A small diamond resting against the skin at room temperature feels noticeably cold precisely because it conducts heat away from the surface so efficiently. Many natural diamonds carry small inclusions, microscopic fragments of other minerals trapped within the crystal during growth. From the standpoint of geological research, these inclusions are remarkable objects. They preserve samples of the mantle environment that existed when the diamond was growing, sometimes hundreds of millions of years ago. The chemical composition of these inclusions, analyzed through mass spectrometry and other techniques, provides information about the temperature, pressure, and chemical conditions in Earth's deep interior at the time of the diamond's formation. Diamonds reach Earth's surface through a geologically rare type of volcanic eruption called a kimberlite eruption. Kimberlite is a type of igneous rock that originates from great depths, reaching into the upper mantle, and rises rapidly to the surface through narrow, pipe-like conduits. According to geological estimates, the ascent is rapid enough to prevent the diamond from reverting to graphite during decompression. Kimberlite pipes are the primary source of mined diamonds. They are distinguished by their circular cross-sections at the surface and their carrot-like form, tapering with depth. High pressure does not act on carbon alone. Many minerals undergo structural transitions at depth, their atoms reorganizing into more tightly packed configurations. These are called high-pressure polymorphs. Olivine, the mineral stable in the upper mantle, transforms at approximately 410 kilometers depth into a denser structure called wadsleyite. Deeper still, at around 520 kilometers, it converts into ringwoodite, a spinel-structured polymorph of the same chemical formula, but a different atomic arrangement. According to seismological data, these transitions correspond to sharp changes in seismic wave velocity at specific depths. At depths approaching the lower mantle, below roughly 660 kilometers, the dominant silicate mineral is believed to be bridgmanite, a magnesium-iron silicate with a perovskite crystal structure. In the perovskite structure, silicon atoms are surrounded by 6 oxygen atoms rather than 4, a shift from tetrahedral to octahedral coordination that reduces volume and accommodates higher pressure. According to current geophysical models, bridgmanite is thought to be the most abundant mineral on Earth by volume, constituting a large fraction of the lower mantle. The mantle, the layer between the crust and the outer core, is composed of solid rock by every geochemical definition. Yet, according to geophysical models built from seismic data, it behaves, over geological timescales, much like an extremely viscous fluid. This is not a contradiction. It is a consequence of the timescales involved. Over millions of years, solid mantle rock deforms through a process called solid-state creep, in which atoms migrate gradually through the crystal lattice rather than the material melting. The result is a very slow circulation of large rock masses within the mantle, carrying heat from depth toward the surface. It is worth sitting with the timescales on which solid-state mantle creep operates, not because they demand comprehension, but because their sheer magnitude is structurally appropriate to the kind of mental slowing this narration is designed to support. Geodynamic models estimate the average residence time of a parcel of mantle rock through a single convective cycle, descending from near the base of the lithosphere into the lower mantle and eventually returning, at between 100 million and 500 million years, depending on the model and the depth assumed. Throughout that entire journey, the rock does not melt, it does not fracture. It deforms through the microscopic movement of atom-scale defects through the crystal lattice, one row shifting past another at a rate so slow that no instrument would register it across a human lifetime. The velocity of mantle convection, the actual speed at which the rock moves, is estimated from plate tectonics and geophysical models at a few centimeters per year for the fastest moving portions of the upper mantle. This is comparable to the rate at which human fingernails grow. A volume of rock the size of a large building moves 1 fingernail thickness in a year. Over 100 million years, that same volume may travel several thousand kilometers across an ocean basin and back, or from the base of the lithosphere to the core mantle boundary and halfway back. The motion is real, measurable in its consequences, but operating at a pace that makes geological time feel less like a number and more like an entirely different category of experience. Rock offers no active resistance to this movement. It simply deforms at whatever rate temperature, pressure, and its own atomic defect density permit. No part of this process is in a hurry. No part of it ever has been. One mechanism of solid-state creep is called dislocation creep. Within a crystal under stress, linear defects called dislocations, rows of atoms slightly displaced from their ideal lattice positions, can move through the crystal by progressively breaking and reforming bonds with neighboring atomic planes. The movement of a single dislocation through a crystal is equivalent to one atomic plane sliding past another. Billions of such microscopic slippages accumulated over long periods produce measurable deformation of rock at geological scale. The viscosity of silicate minerals in the mantle, their resistance to flow, varies with temperature. At higher temperatures, atomic bonds break and reform more readily, allowing dislocations to move more easily and deformation to occur more readily. At lower temperatures, the same material flows far more slowly. This temperature dependence of viscosity means that cold, subducting oceanic lithosphere is considerably stiffer than the warmer mantle surrounding it, creating the mechanical contrasts that govern the geometry of convection. Water, in trace amounts, plays a role in mantle rheology that is disproportionate to the small quantities involved, according to experimental petrology data. Even parts per million concentrations of water incorporated into mantle minerals can reduce their effective viscosity significantly. Water weakens mineral lattices by introducing hydroxyl groups, OH units, into structural positions within the crystal, disrupting the regularity of bonding and facilitating dislocation movement. This is one of the reasons why the presence of water, even at depth, is considered significant in understanding the mechanical behavior of the mantle. The deep earth processes described here cannot be directly observed. No instrument has sampled the mantle in place. What is known, and a great deal is known, comes from seismic measurements, high-pressure laboratory experiments, and chemical analysis of rock brought to the surface by geological processes. These are indirect measurements of an indirect world. Their conclusions, according to scientific consensus, are considered reliable within certain margins of uncertainty. When oceanic crust, cold, dense basaltic, travels across the ocean floor and eventually meets another tectonic plate at a convergent boundary, it begins its descent back into the mantle. This process is called subduction. The descending plate carries with it not only cold, rigid rock, but also water locked within hydrated minerals, serpentinite, chlorite, amphibole. As the plate sinks and pressure increases, these minerals undergo dehydration reactions, releasing their structural water as a fluid that rises into the overlying mantle wedge. The introduction of that water lowers the melting point of the mantle rock, triggering partial melting and ultimately generating the magma that feeds the volcanic arcs sitting above subduction zones. Under the high pressures reached during subduction, basaltic oceanic crust transforms mineralogically into a dense rock type called eclogite. This transformation involves the replacement of plagioclase feldspar by garnet and omphacite, a sodium-rich pyroxene, both of which are stable at high pressures. Eclogite is considerably denser than the original basalt, and this increased density is, according to geodynamic models, one of the principal forces pulling the plate downward. Eclogite xenoliths, fragments of this deep rock, are occasionally brought to the surface within kimberlite pipes, providing direct samples of high-pressure mineral assemblages. Some minerals brought rapidly to the surface during volcanic or tectonic events cannot convert to their surface-stable equivalents before cooling prevents further atomic rearrangement. These are called metastable phases, structures existing outside their thermodynamic stability field because insufficient energy is available to trigger the transition. Coesite, the high-pressure form of silicon dioxide, has been found preserved within impact craters and within eclogite xenoliths brought up from depth. Its presence in a rock is considered strong evidence that those minerals once existed under high-pressure conditions. At approximately 660 kilometers depth, seismological studies detect a sharp discontinuity in wave velocities. This boundary, known as the 660-kilometer discontinuity, corresponds to a phase transition in which ringwoodite, the high-pressure polymorph of olivine, breaks down into bridgmanite and ferropericlase. The volume change associated with this transformation is relatively modest, but significant enough to affect the density structure of the mantle at that depth and, according to some geodynamic models, to partially impede the passage of subducting slabs across it. At the atomic level, applying pressure to a mineral reduces the distances between atoms. As interatomic distances decrease, the electron orbitals of neighboring atoms begin to overlap more extensively. This increased orbital overlap modifies the nature of chemical bonding. Transitions from predominantly ionic to more covalent character under extreme pressure have been documented in some minerals. The electronic structure of an atom and the way its electrons occupy orbital shells responds to the compression that pressure imposes. The bulk modulus of a mineral, sometimes called incompressibility, quantifies how much pressure is required to reduce its volume by a given fraction. Diamond's bulk modulus is exceptionally high, approximately 442 gigapascals, meaning it resists compression strongly. For comparison, olivine at surface conditions has a bulk modulus of roughly 130 gigapascals. These values, measured experimentally using diamond anvil cells, devices capable of generating pressures equivalent to those at significant mantle depths, provide essential data for modeling seismic wave velocities throughout Earth's interior. The shear modulus, resistance to a change in shape rather than volume, is the other key elastic constant governing seismic wave propagation. The velocity of a compression wave through a mineral depends on both the bulk modulus and the shear modulus. The velocity of a shear wave depends on the shear modulus alone. By measuring seismic wave velocities at various depths and comparing them against laboratory data for candidate minerals, geophysicists construct models of which minerals are present at every depth within the mantle. At the very base of the mantle, in the layer sitting immediately above the core mantle boundary, known as the DLL layer, another mineral transition takes place. Bridgmanite, which dominates the lower mantle, transforms under the extreme conditions at this depth into an even denser structure called post-perovskite. Discovered experimentally in 2004, this transition is associated with a seismic discontinuity that had previously been detected but not explained. Post-perovskite has a layered crystal structure that may influence how heat flows across the core mantle boundary. Iron is present throughout the mantle, not as pure metal, but as iron ions, Fe2+ and Fe3+, substituting for magnesium or other cations within silicate mineral lattices. The behavior of iron at depth is more complex than at the surface because pressure modifies the electron configuration of iron ions through a process called a pressure-induced spin transition. Under surface conditions, iron in many minerals exists in a high spin state, with electrons distributed across d orbitals in a way that maximizes spatial occupancy. Under high pressure, iron transitions to a low spin state, in which electrons pair more compactly, reducing the effective size of the iron ion. This spin transition in iron, experimentally documented using synchrotron X-ray methods in diamond anvil cells over the past 2 decades, affects the density, compressibility, and thermal conductivity of mantle minerals. The depth at which this transition occurs within Earth, estimated to be somewhere in the mid to lower mantle, may subtly influence seismic wave characteristics in that region. According to current research, the full geodynamic consequences of this transition remain an active area of investigation. With increasing depth through the mantle, mineral densities rise progressively, partly through compression under higher pressure, and partly through phase transitions to denser crystal structures. Mineral densities at the base of the mantle are considerably greater than those at the surface. This density gradient is not a smooth, continuous change. It includes step-like increases at phase transition depths that show up in seismic data as abrupt shifts in wave velocity. Water appears simple at first glance. Two hydrogen atoms bonded to one oxygen. A molecule almost vanishingly small beside the scale of the minerals it encounters. And yet, according to all available chemical data, it ranks among the most chemically active substances on Earth's surface, not because it is aggressive in any dramatic sense, but because of a structural property that gives it an almost universal affinity for other molecules. The water molecule is electrically asymmetric. Oxygen, being more electronegative than hydrogen, draws the shared electron pairs in each OH bond toward itself. The result is that the oxygen end of the molecule carries a partial negative charge, while each hydrogen end carries a partial positive charge. This charge separation, the dipole, is not merely a detail. It is the source of nearly every anomalous property water possesses. Water's dipole moment at approximately 1.85 dBs places it among the more polar small molecules found in nature. Because water molecules are dipolar, they attract one another. The positive hydrogen of one molecule is drawn toward the negative oxygen of a neighboring molecule. This attraction, called a hydrogen bond, is not a covalent bond. It is weaker, more flexible. It breaks and reforms continuously as molecules move past one another. According to X-ray and neutron scattering data, in liquid water at room temperature, each molecule participates in an average of approximately 3.4 hydrogen bonds. The result is a constantly shifting three-dimensional network of transient bonds that gives water its anomalously high surface tension, high boiling point, and high specific heat capacity relative to its molecular weight. When water encounters a mineral surface, its dipolar structure allows it to interact directly with the exposed ions on the crystal face. The negative oxygen end of the water molecule orients toward positively charged metal cations on the mineral surface. The positive hydrogen ends orient toward exposed oxygen anions. This directed arrangement of water molecules around ions, called hydration, effectively weakens the bonds holding those ions within the crystal lattice. Over time, individual atoms are pulled free from the crystal surface and carried into solution, surrounded by shells of oriented water molecules. This, in simplified terms, is how water dissolves minerals. In the case of salt, sodium chloride, NaCl, the dissolution process has been studied in considerable detail. In the solid crystal, sodium ions, Na+, and chloride ions, Cl-, are held in an alternating cubic lattice by electrostatic attraction. When immersed in water, molecules at the crystal surface become surrounded by water molecules. Water's oxygen end clusters around sodium ions. The hydrogen ends cluster around chloride ions. The energy released by these hydration interactions is sufficient under normal conditions to overcome the lattice energy holding the crystal together. Ions detach from the surface and enter solution. Water's capacity to dissolve ionic compounds is quantified in part by its dielectric constant, a measure of how much it reduces the electrostatic force between two charges. At 25 degrees Celsius, water's dielectric constant is approximately 78.4, exceptionally high for a small molecule. This high dielectric constant means that when ions are in solution, the attractive force between oppositely charged ions is reduced by roughly a factor of 78 relative to what those same ions would experience in a vacuum. That reduction keeps ions separated in solution rather than immediately recombining. At hydrothermal vents on the ocean floor, where seawater percolates down through fractures into the oceanic crust, is heated by the magma beneath and returns to the ocean floor. The chemistry of mineral dissolution and precipitation operates at an accelerated pace. Heated seawater, sometimes reaching several hundred degrees Celsius while remaining liquid under the pressure of the deep ocean, dissolves metals and sulfur compounds from the surrounding basalt far more rapidly than cold seawater could. When this superheated fluid exits a vent chimney and mixes with cold seawater, the abrupt change in temperature and chemistry causes dissolved minerals to precipitate rapidly, building the characteristic sulfide chimneys of black smoker vents. The precipitation of calcium carbonate, the formation of limestone and related materials from dissolved calcium and carbonate ions in water, proceeds at a rate that depends on the degree of supersaturation of the solution. When the concentrations of calcium ions, Ca2+, and carbonate ions, CO3 in solution, exceed the solubility product of calcium carbonate, precipitation becomes thermodynamically favorable. The actual rate of precipitation also depends on temperature, pH, the presence of inhibiting ions, and the availability of nucleation sites, surfaces on which crystal growth can begin. Mineral precipitation from hydrothermal fluids at deep-sea vents is, in terms of reaction rates, among the fastest mineral-forming processes documented in the geological record. At a black smoker vent, the mixing of 350 degrees Celsius vent fluid with near freezing seawater occurs across a distance of centimeters. The temperature change within that mixing zone exceeds 300 degrees across a spatial interval measurable in millimeters. Chemical equilibria that would take decades to shift in a slowly cooling geological system change within seconds in the vent mixing zone. The result is that minerals precipitate not as well-formed crystals with time to properly organize their lattices, but as extremely fine-grained, poorly crystalline aggregates, sometimes called amorphous or nanocrystalline phases, that record the kinetic conditions of rapid precipitation far more faithfully than they approach the thermodynamic ideal of slow, orderly crystal growth. Chalcopyrite, CuFeS2, pyrite, Fes2, pyrrhotite, Fe1-XS, sphalerite, Zns, and wurtzite, another polymorph of zinc sulfide, all precipitate within and around black smoker chimneys. The specific mineral assemblage at any given vent reflects the composition of the source fluid, which in turn reflects the composition of the basaltic crust through which the hydrothermal circulation has moved. Vents in basalt-hosted systems tend to produce copper-iron-zinc sulfide chimneys. Vents in ultramafic systems produce different assemblages, often richer in nickel and cobalt sulfides. Chimney walls sampled, sectioned, and analyzed for research reveal concentric mineralogical zonation. High-temperature sulfide minerals closest to the fluid channel, grading outward toward the cooler outer wall, where mixing with seawater is more complete, into lower-temperature minerals and anhydrite, a calcium sulfate. This zonation is a frozen record of the temperature gradient within the chimney wall at the moment of deposition. The carbonate system in seawater is, according to ocean chemistry data, a buffered system. Carbon dioxide, dissolved from the atmosphere, reacts with water to form carbonic acid, H2CO3, which partially dissociates into bicarbonate, HCO3- and carbonate, CO3 ions. The relative proportions of these species in solution depend on pH. At the pH of typical surface seawater, approximately 8.1, bicarbonate is the dominant carbonate species. In deeper, more acidic waters, carbonate ion concentrations decrease, reducing the degree of saturation with respect to calcium carbonate. The pH of a solution, its hydrogen ion concentration, directly governs the solubility of many minerals. Minerals containing carbonate, hydroxide, or oxide groups tend to dissolve more readily under acidic conditions, where excess hydrogen ions react with the mineral surface. Silica, quartz, and the amorphous forms of SiO2 is relatively insoluble under acidic conditions, but dissolves more readily in alkaline environments. This pH dependence means that the chemical evolution of a body of water has a substantial influence on which minerals dissolve, are transported, and ultimately precipitate elsewhere. In alkaline hydrothermal systems, those associated with the serpentinization of ultramafic rocks, where water reacts with olivine and generates strongly alkaline fluids, silica from the surrounding rock dissolves readily and is carried by the circulating fluid. When that silica-rich fluid encounters cooler conditions or a change in chemistry, it can precipitate as chalcedony, opal, or other silica phases. The resulting silica deposits, found as veins cutting through altered ultramafic rock, record the pathways of ancient fluid flow preserved in crystalline form. Hydrothermal alteration refers broadly to the chemical modification of rock by hot, chemically active fluids. When hot water percolates through fractures in basalt, it reacts with primary minerals, olivine, pyroxene, plagioclase, converting them into secondary minerals that are more stable under lower temperature, water-rich conditions. Olivine converts to serpentine, plagioclase to zeolites at lower temperatures, or to epidote and cerussite at higher temperatures, while calcite precipitates separately in fractures and void spaces from the calcium-bearing fluids released during these reactions. These reactions are thermodynamically exothermic. They release heat. According to geochemical calculations, the serpentinization of olivine-rich rock releases sufficient heat to sustain microbial activity within the rock long after the original hydrothermal circulation has ceased. Zeolites are a family of aluminosilicate minerals with a distinctive open framework structure. Silicon oxygen and aluminum oxygen tetrahedra link together to form rings and channels, creating a porous three-dimensional architecture with cavities large enough to accommodate water molecules and certain cations. These internal channels give zeolites their well-documented ion exchange and molecular sieving capacity. In geological settings, zeolites form in the pore spaces of volcanic tuff and altered basalt through which silica-rich alkaline fluids circulate at low temperatures. Their internal surface area, large relative to their external dimensions, allows them to interact extensively with fluids passing through them. When a mineral precipitates from a supersaturated solution, it does not simply appear. The process begins with nucleation, the formation of a small cluster of ions or molecules that serves as a seed for subsequent crystal growth. Homogeneous nucleation in a perfectly clean solution requires a degree of supersaturation that is rarely achieved in natural waters. In practice, nucleation almost always occurs on a pre-existing surface, a dust particle, a crystal face, a scratch on the wall of a vessel, a process called heterogeneous nucleation, which requires less energy and occurs at lower degrees of supersaturation. 63 details in, and water has not been hurried. It has always moved through rock at the pace water moves through rock, too slow to follow in real time, but fast enough across millions of years to dissolve and redeposit the minerals of entire mountain ranges somewhere else entirely. In regions of the mantle, where rock flows under directional stress over long periods, such as in the mantle wedge above a subduction zone, or within the deep roots of rapidly moving tectonic plates, minerals develop a preferred orientation. Rather than being randomly distributed in space, the crystallographic axes of individual mineral grains tend to align with the direction of flow. This alignment, called lattice preferred orientation, affects how seismic waves move through the rock. Waves traveling in the flow direction propagate at a slightly different velocity than those traveling perpendicular to it. Seismologists use this anisotropy to map mantle flow patterns at depth. 50 details into the deep interior, and no pause is required here. These details ask nothing of memory. They simply exist, layer upon layer, far beneath the surface of any continent or ocean floor, the way the minerals themselves simply exist. We continue through the video, slowly and without pause. These slow processes are best imagined at a slow pace. Once nucleation has occurred and a crystal seed exists within a supersaturated solution, growth proceeds through the addition of ions or molecules from the solution onto the crystal surface. The rate of this growth is governed by several factors: the degree of supersaturation, temperature, and the availability of favorable bonding sites on the crystal surface. Crystal faces bearing surface steps, sites where an exposed edge of the lattice exists, grow more readily than atomically flat surfaces because attaching an ion to a step requires forming fewer new bonds than attaching it to a flat face. Stalactites, the mineral formations hanging from cave ceilings, are columns of calcium carbonate deposited incrementally from supersaturated water. As water percolates through the limestone above a cave, it acquires dissolved calcium and bicarbonate, arrives at the cave ceiling, and hangs for a moment as a droplet. During that brief suspension, carbon dioxide is partially released from the water into the cave atmosphere as a gas. The loss of CO2 shifts the carbonate equilibrium, increasing the degree of saturation with respect to calcite. Calcite precipitates across the surface of the formation as water flows slowly over it, layer upon layer, droplet after droplet. Over thousands of years, these incremental deposits accumulate into the tapered, solid columns characteristic of active cave systems. A slender subtype called a soda straw stalactite does grow as a hollow tube, calcite rings precipitating at the edge of each droplet before it falls. But these eventually transition into conventional stalactites when their central canal becomes blocked and water begins flowing over the outer surface instead. The growth rate of stalactites has been measured through precise laser distance measurements in active cave systems and through the dating of thin calcite layers using uranium-thorium isotopic methods. Growth rates vary considerably between cave systems and even between individual stalactites within the same cave because they depend on the flux of water reaching the cave ceiling, the partial pressure of carbon dioxide in the cave atmosphere relative to the overlying soil, and the degree of supersaturation of the drip water with respect to calcite. Measured growth rates range from less than 1/10 of a millimeter per year to several millimeters per year under the most favorable conditions. A stalactite 1 meter in length may therefore represent anywhere from a few thousand years of incremental growth to several 100,000. Uranium is incorporated in trace amounts into stalactite calcite at the time of deposition, always at a concentration low enough not to affect the crystal structure, but measurable by mass spectrometry. Thorium, which is insoluble in water, is not incorporated. After deposition, the uranium within the calcite decays to thorium at a known rate. The uranium-thorium ratio in any given layer of the stalactite is therefore a direct measure of the time elapsed since that layer was deposited, a radiometric clock set into the crystal structure at the moment of precipitation. This dating method, known as uranium-thorium dating, yields ages accurate to roughly 1 to 2% in well-preserved samples that have remained closed chemical systems, accuracy that can decrease when detrital thorium contamination is present, as it commonly is in cave environments, making it one of the more precise chronological tools available for materials that formed under surface conditions and have remained chemically closed systems since deposition. In this sense, a stalactite is not merely a mineral formation. It is a self-sufficient archive of past climate and past time alike, written in calcium carbonate without requiring any attention or intention from the mineral itself. Speleothems, the collective term for cave mineral deposits, including stalactites, stalagmites, and flowstones, preserve a chemical record of past climates within their layered structures. As water seeping through the rock above absorbs carbon dioxide from the soil, the CO2 concentration in that water reflects the activity of soil microbes and plant roots above, which in turn reflects surface temperature, rainfall, and vegetation cover. The ratio of oxygen isotopes incorporated into calcite at the time of deposition varies with the temperature and source of the water. By measuring these isotopic signatures layer by layer through a speleothem, researchers reconstruct past climate conditions at resolutions ranging from seasonal to decadal. Water in rock pores does not simply sit still. Forces act on it from the pore walls. Surface tension at air-water interfaces within narrow pores generates capillary pressure, drawing water upward against gravity and holding it within the pore structure. In very fine-grained rocks, capillary forces can be substantial. The height to which water rises in a capillary tube, and by analogy within a narrow rock pore, is inversely proportional to the radius of the tube. The smaller the pore, the greater the capillary rise. In fine-grained chalk, water can be held against gravity at heights that would be impossible in coarser rock. In climates where temperature cycles around the freezing point of water, the expansion of freezing water within rock pores and fractures can exert pressures on the surrounding rock that exceed the tensile strength of many mineral assemblages. Water expands by approximately 9% in volume when it freezes. That expansion within a sealed pore or fracture generates pressure, the magnitude of which depends on the geometry of the void and the rate of freezing. Repeated freeze-thaw cycles progressively widen fractures, producing the angular, shattered rock fragments characteristic of cold climate landscapes. The chemical weathering of feldspar is one of the most geochemically significant processes operating at Earth's surface. When feldspar is exposed to water carrying dissolved carbon dioxide, forming a dilute solution of carbonic acid, the mildly acidic water donates protons to the feldspar surface, breaking aluminum-oxygen bonds and releasing aluminum, silicon, and metal cations into solution. The residual silica framework reorganizes into clay minerals, layered aluminosilicates, related to mica but with far smaller grain size. This transformation releases cations into rivers and ultimately into the oceans, contributing to the global geochemical cycles of calcium, potassium, sodium, and silicon. Kaolinite, one of the most common clay minerals, carries the chemical formula Al2Si2O5OH4. It forms most readily in hot, humid, intensely leached environments, tropical and subtropical weathering profiles, where persistent rainfall continually removes mobile cations, leaving behind aluminum and silicon. The crystal structure of kaolinite consists of paired layers, a silicate tetrahedral sheet bonded to an aluminum hydroxide octahedral sheet. These paired units stack together, held by hydrogen bonds between them, bonds strong enough to maintain coherence, but weak enough to allow kaolinite particles to be soft and to disaggregate readily in water. Clay minerals, unlike most other silicate minerals, carry a net negative charge on their basal surfaces, a consequence of the substitution of higher valence ions by lower valence ions within the lattice. This charge imbalance is compensated by the adsorption of cations from solution onto the clay surface. These adsorbed cations can be exchanged for other cations present in solution, a property called cation exchange capacity. Soils rich in clay minerals have higher cation exchange capacity, meaning they retain more nutrient cations against leaching by rainfall. Organic acids produced by the decomposition of organic matter in soil and by root exudates from plants contribute to the chemical dissolution of minerals in a process that overlaps with purely inorganic weathering. Oxalic acid, citric acid, and other organic ligands are effective at dissolving iron and aluminum from mineral surfaces through a process called ligand-promoted dissolution. The organic molecule binds directly to the metal ion at the mineral surface, weakening its attachment to the lattice and facilitating its release into solution. The organometallic complexes that result are soluble and mobile in soil water. Groundwater, water moving slowly through the pore spaces and fractures of subsurface rock, acquires its chemical character gradually as it flows through the geological environment. Near the surface, where fresh recharge dominates, groundwater is relatively dilute and mildly acidic from dissolved carbon dioxide. At greater depth, after longer contact with rock, it becomes more mineralized. Calcium, magnesium, sodium, potassium, bicarbonate, and sulfate concentrations rise as ions are released from mineral surfaces. Springs issuing from limestone aquifers are typically rich in calcium and bicarbonate, the direct chemical signature of the limestone through which the water has traveled. In basins where water input exceeds outflow and no drainage to the sea exists, evaporation progressively concentrates the dissolved ions in the remaining water. As evaporation continues, the solution eventually reaches saturation with respect to certain minerals, which then precipitate sequentially according to their solubility. Gypsum, calcium sulfate dihydrate, precipitates before halite, sodium chloride, which precipitates before the more soluble potassium and magnesium salts. The resulting succession of evaporite layers records the chemical evolution of an ancient water body long since vanished. Brine, water with dissolved salt concentrations well above that of seawater, exhibits chemical and physical properties that differ substantially from pure water. Its density is higher, its freezing point is depressed, its vapor pressure is lower. Its capacity to dissolve additional minerals depends on competitive interactions between the various ions already in solution. In subsurface brines trapped within sedimentary basins over millions of years, the chemistry can become extraordinarily complex, carrying dissolved metals, organic compounds, and rare elements at concentrations far exceeding those of normal groundwater. These ancient brines are, geochemically, among the most compositionally diverse natural fluids found on Earth. 75 details have passed through this narration the way water passes through fractured limestone, not all at once, but gradually, percolating through each layer in turn. What remains belongs to an entirely different category of matter: metals, insoluble, uncorroded, not participating in these cycles of dissolution and reprecipitation the way silicates and carbonates do, persisting simply by virtue of their electronic structure. There is a category of metals that chemists and metallurgists place at the top of what is known as the electrochemical series, a ranking that orders elements according to their tendency to lose electrons and form ions in solution. At the lower end of that series sit metals that oxidize readily: sodium, calcium, magnesium. At the upper end sit metals whose tendency to ionize is so low that they persist on Earth's surface in their elemental, metallic state across timescales that overlap with geological processes. These are the noble metals: gold, platinum, palladium, rhodium, iridium, osmium, and a handful of others. According to quantum chemical theory, gold's unusual chemical stability is not a simple property. It is a consequence of relativistic effects, the fact that electrons in the innermost orbitals of heavy atoms like gold move at speeds that constitute a significant fraction of the speed of light. At those speeds, relativistic physics predicts that electrons gain mass and their orbitals contract. For gold, this contraction acts disproportionately on the 6s orbital, pulling the 6s electrons closer to the nucleus, lowering their energy and making them less available for chemical bonding. The result is that gold's outermost electrons are held more tightly than non-relativistic chemistry would predict. Gold's resistance to oxidation is a direct consequence of this electron configuration. For a metal to oxidize, to lose its electrons to an oxidizing agent, such as oxygen, the energy cost of removing those electrons from the atom must be lower than the energy gained from forming the resulting oxide compound. For gold, the relativistically contracted 6s orbital raises the ionization energy to a point where the energy gained from forming a gold oxide does not cover the cost. Gold oxide is thermodynamically unstable under surface conditions. This calculation, built into the atom's own electronic structure, is why gold surfaces remain bright thousands of years later. The platinum group metals, platinum, palladium, rhodium, ruthenium, iridium, and osmium, share with gold a high position in the electrochemical series, and with it a resistance to corrosion under most surface conditions. Their stability is rooted in the electronic structure of their d orbitals, partially filled in configurations that do not readily donate electrons to oxidizing agents in these heavy elements. Platinum, in particular, resists attack by two of the most aggressive mineral acids individually, hydrochloric acid and nitric acid, though their mixture, aqua regia, ultimately dissolves it through complex ligand chemistry involving chloride ions. Platinum crystallizes in a face-centered cubic structure, the same crystal system as gold, silver, copper, and many other metals. In the face-centered cubic arrangement, metal atoms occupy the corners and face centers of each unit cell. This packing geometry achieves a theoretical packing efficiency of approximately 74%, close to the maximum possible for equal-sized spheres. The resulting structure is both dense and mechanically ductile. The closely packed planes of atoms can slide past one another under stress without the crystal fracturing, which is why platinum, like gold, can be drawn into fine wire or rolled into thin sheet. Gold's remarkable malleability, its ability to be hammered into extraordinarily thin sheets without fracturing, is a consequence of how readily the atomic planes in the face-centered cubic lattice slide past one another under mechanical stress. The dislocations responsible for this plastic deformation move with gold with relatively little energy, because the stacking fault energy, the energy cost of temporarily disrupting the regular stacking sequence of atomic planes during dislocation motion, is low. 1 gram of gold can theoretically be beaten into a sheet covering approximately 1 square meter. At that point, the sheet may be only a few hundred atoms thick. The electrochemical series is a formal ranking of reduction potentials, the tendency of an element in solution to accept electrons and return to its elemental state. Gold's standard reduction potential for the Au3+ Au couple is approximately plus 1.52 volts. For reference, hydrogen is assigned 0 volts by convention. Zinc, which oxidizes readily, sits at negative 0.76 volts. A higher positive potential indicates a stronger tendency to remain in the reduced metallic state. Gold's high positive potential means that most common oxidizing agents present in surface environments, atmospheric oxygen, water, are thermodynamically incapable of oxidizing it under normal conditions. Osmium, the densest naturally occurring element, has a density of approximately 22.59 grams per cubic centimeter under standard conditions, marginally higher than its nearest rival, iridium, at approximately 22.56 grams per cubic centimeter. Iridium's extraordinary density is a consequence of both its heavy atomic mass and its compact face-centered cubic crystal structure, which packs heavy atoms together with high efficiency. It is also exceptionally hard and carries a melting point of approximately 2,443 degrees Celsius. Some metals that are not intrinsically noble develop surface stability through the spontaneous formation of a thin, adherent oxide layer that protects the underlying metal from further reaction. This process is called passivation. Aluminum is the most familiar example. It is intrinsically reactive, yet its surface forms an amorphous oxide layer only a few nanometers thick that effectively prevents further oxidation. The oxide layer is transparent, chemically stable under most conditions, and strongly adherent. It does not flake away the way rust does on iron. Titanium and chromium similarly rely on passivation for their surface stability, which is why stainless steel, which contains significant chromium, resists corrosion despite being substantially iron. The passivation layer on aluminum repays closer examination at the molecular level because its effectiveness is disproportionate to its thinness. The spontaneously forming oxide layer on aluminum exposed to air, amorphous aluminum oxide, Al2O3, is typically 2 to 10 nanometers thick. A nanometer is 1/1000th of a meter. The layer is invisible in any practical sense, undetectable by touch, and does not alter the visible appearance of the metal. Yet because of that film, only a few atomic layers deep, aluminum atoms are fully coordinated by oxygen. Each aluminum ion is surrounded by oxygen ions in a stable octahedral arrangement, with no reactive aluminum metal bonds remaining exposed to the atmosphere. The film is self-limiting. Once oxygen can no longer reach the underlying metal, the growth of the oxide layer stops. When the film is scratched, it repairs itself spontaneously because freshly exposed aluminum reacts immediately with atmospheric oxygen or water vapor, reforming the protective layer within milliseconds. The energy driving this rapid repair is the strongly negative free energy of aluminum oxide formation. Aluminum has a very high affinity for oxygen, and this is what, paradoxically, makes it one of the more durable structural metals under ambient conditions. The same thermodynamic affinity that would cause aluminum to corrode aggressively in the absence of the passivation layer is precisely what makes that layer so stable once it has formed. Iron lacks this self-repair capacity because iron oxide, rust, is not adherent. Rather than sealing the surface, it flakes away, continually exposing fresh metal. The difference is structural. Iron oxide does not bond to the underlying iron surface with the same geometric compatibility that aluminum oxide achieves with its substrate. Silver occupies a different position in the electrochemical series from gold. Its standard reduction potential is approximately plus 0.80 volts, positive, indicating nobility, but considerably below gold's plus 1.52 volts. As a result, silver is thermodynamically susceptible to attack by trace sulfur compounds present in air. Silver tarnish, the dark coating that develops on silver surfaces exposed to air over time, is silver sulfide, Ag2S, formed by silver's reaction with trace hydrogen sulfide or other sulfur species. The reaction is slow, but it demonstrates that silver's nobility carries practical limits under ambient conditions, unlike that of gold. Lower on the nobility scale, copper, with a standard reduction potential of approximately plus 0.34 volts, reacts with atmospheric oxygen, water, and carbon dioxide over years to decades, developing the characteristic green patina composed of a mixture of copper carbonates and hydroxides, primarily malachite and azurite. Once formed, this patina is chemically stable and functions as a protective layer that slows subsequent corrosion. The green copper roofs of historic buildings in temperate, humid climates are the macroscopic expression of this surface chemistry, operating at the level of individual ions reacting with atmospheric gases on the copper surface. Gold and platinum form in geological settings where their chemical stability ensures that the dissolution processes governing other metals do not carry them away. Native gold, metallic gold in elemental form, is found in quartz veins formed when hydrothermal fluids cooled and deposited their dissolved mineral content. The gold in these veins precipitated from hydrothermal fluids in which it had been complexed with bisulfide or chloride ligands, a rare condition capable of dissolving it, and deposited in metallic form when those complexes became thermodynamically unstable. Gold nuggets found in hydrothermal vein systems are not simply chunks of crystallized gold from solution. Their internal structure, revealed by careful polishing and microscopy, tells a complex history. Primary crystalline gold with dendritic or fibrous texture from the initial deposition, overlaid by subsequent layers of coarser crystalline gold, the whole cross-cut by fractures, later healed with additional gold deposition. This layered structure records multiple episodes of fluid flow and gold precipitation across the history of the hydrothermal system. Placer gold, the rounded, water-worn gold particles found in river gravels, represents primarily a secondary concentration of gold, originally dispersed through hydrothermal veins and the surrounding host rock. As weathering and erosion break down the rock, gold, chemically inert under surface conditions, is released as individual particles. being far denser than quartz and other common minerals, density approximately 19.3 grams per cubic centimeter versus approximately 2.65 grams per cubic centimeter for quartz. Gold preferentially settles in river sediments wherever flow velocity decreases, on the downstream side of large boulders, on the inner bends of meanders, in the quiet water behind submerged bars. Gravity, acting on density, concentrates gold without any chemical process involved. 88 details have accumulated through this narration the way sediment accumulates in still water, slowly, layer by layer, each one adding to the density of what came before without disturbing it. The final 12 belong to the same theme, the persistence of noble matter across geological time, and the quiet atomic reasons for that persistence. And so we approach the end, slowly and without hurry. I hope the information in this video has been both useful to you and helpful in easing you toward sleep. What I wanted, in complete sincerity, was simply to make something of genuine quality, something that might also let you rest. Let's continue. Platinum's resistance to chemical attack extends to environments that qualify as aggressively acidic by geological standards. In hydrothermal systems that generate strongly acidic brines, sulfate-rich fluids produced by the oxidation of sulfide minerals, platinum remains in its elemental state where most other metals dissolve and are carried away in solution as ions. This exceptional stability means platinum tends to remain concentrated at or near its original geological formation site, rather than being redistributed by fluid flow, which is one reason platinum deposits are comparatively localized and geographically rare. Osmium, which competes with iridium for the distinction of being the densest naturally occurring element, is also among the hardest of all metals and carries the highest melting point of the platinum group elements, approximately 3033 degrees Celsius. Its crystal structure is hexagonal close-packed, distinct from the face-centered cubic structure of platinum and gold. And this structural anisotropy gives it directional differences in mechanical properties. In geological settings, osmium occurs not as pure metal, but predominantly as an alloy with iridium, known as osmiridium. Rhodium is among the rarest of the platinum group metals, and under surface conditions, among the most resistant to corrosion, more so than silver or copper under ambient conditions. Rhodium is recovered almost exclusively as a byproduct of platinum and palladium mining. Its geological scarcity reflects both a low average crustal abundance, estimated at a few parts per billion, and a tendency to remain concentrated in the original magmatic source rocks, rather than being redistributed by weathering. Palladium, unlike its platinum group relatives, possesses an unusual chemical property. It absorbs hydrogen gas with extraordinary capacity. At room temperature, palladium metal can absorb up to 900 times its own volume of hydrogen gas. Hydrogen atoms occupy interstitial sites, the spaces between metal atoms, within the face-centered cubic palladium lattice, without fundamentally disrupting the crystal structure. The hydrogen atoms within the lattice retain a degree of mobility, diffusing through the metal along interstitial pathways. This property has been extensively studied in material science research related to hydrogen storage applications. Gold objects recovered from ancient contexts, Egyptian jewelry, Scythian ornaments, Mesoamerican artifacts, preserve their surface condition with a fidelity unmatched among metals. No corrosion, no tarnishing, no structural degradation attributable to simple chemical exposure in a burial environment. Some of the gold surfaces on these objects retain details of the original manufacture, tool marks, surface textures, granulation patterns that would have been obscured by corrosion in any less noble metal. This preservation is a direct consequence of gold's thermodynamic stability, which has not changed between the moment of fabrication and the present day. The concept of electrochemical nobility, a metal's position in the electrochemical series, is not an abstract property. It is the quantitative expression of a specific physical reality, the balance between the energy cost of removing electrons from the metal's atomic orbitals and the energy gained when those electrons combine with an oxidizing agent. Where that balance is determined by the metal retaining its electrons, corrosion does not proceed spontaneously. Noble metals occupy positions in the series where that balance falls decisively on the electron-retaining side, which is the atomic expression of why they persist. The atomic radii of noble metals play a role in their alloying behavior. Gold's atomic radius is approximately 144 picometers. Platinum's approximately 139, palladium's approximately 137. These radii are similar enough that gold, platinum, and palladium can substitute for one another in a crystal lattice without introducing significant strain, allowing alloy compositions across a range of proportions. The degree of mismatch between atomic radii in an alloy, the size mismatch, determines how much the lattice is distorted by substitution, which in turn affects mechanical properties such as hardness and yield strength. Gold crystals, both in natural specimens and laboratory-grown samples, frequently display a structural feature called twinning. Two or more crystal domains grown together at a shared boundary, with their lattice orientations related by a reflection or rotation. In gold, contact twins in which two domain orientations meet at a flat boundary are observed in placer gold grains and in hydrothermally deposited gold. More complex multiple twin structures are observed in very small gold particles at the nanoscale, where surface energy considerations favoring twin formation become geometrically dominant. Gold's characteristic yellow color, distinctive among metals, almost all of which appear gray or silver, is a direct consequence of the same relativistic effects that underpin its chemical stability. The contraction of the 6s orbital raises its energy relative to the 5d orbitals. This energy gap determines which wavelengths of visible light are absorbed when light interacts with the conduction electrons of the metal. For gold, the energy gap corresponds to the energy of blue light, meaning blue wavelengths are preferentially absorbed, and the reflected light is enriched in yellow and red wavelengths. Silver and platinum, with different orbital energy gaps, reflect all visible wavelengths roughly equally, which is why they appear gray-silver. Naturally occurring gold is rarely pure. It almost always contains some silver, the two elements forming a continuous solid solution series called electrum at higher silver contents. The silver content of natural gold varies from a few percent to over 50%, depending on the temperature and chemistry of the hydrothermal fluid from which it precipitated. Higher temperature hydrothermal gold tends to be richer in silver. Supergene gold, gold chemically purified near the surface by weathering processes that preferentially dissolve silver, tends to be purer. A supergene gold nugget may have a bright, high-purity outer zone enriched by selective silver dissolution, overlying an interior that still carries the original silver-bearing composition. Gold deposits persist for extraordinarily long stretches of the geological record. Placer deposits formed by the weathering and erosion of ancient gold-bearing rock can survive as geologically coherent accumulations for hundreds of millions of years, as long as subsequent geological events have not physically disrupted or chemically altered them. The gold within them is unchanged, the same atomic structure, the same purity, the same physical properties as the day it was deposited in the sediment. This persistence is not the result of any exceptional geological preservation of the host sediment. It is the result of the metal's own thermodynamic stability. At the finest possible resolution, at the scale of individual atoms, all 100 subjects share a single underlying commonality. Whether the topic is the interlocking silicon-oxygen tetrahedra of a quartz crystal, the carbon-carbon bonds within a diamond at depth, the hydration shells of ions dissolved in water passing through limestone, or the contracted 6s orbital that makes gold unreactive, every observation is ultimately a description of electrons in specific spatial arrangements around atomic nuclei. The behavior of matter at geological scale, the flow of the mantle, the dissolution of mountains, the accumulation of gold in a riverbed, traces directly from these arrangements, not from history, not from intention, not from any externally imposed narrative, from the geometry of electrons and nuclei operating according to physical laws that are, as far as current scientific data indicates, identical everywhere on the planet and unchanged across the geological timescales these processes encompass. This is the 100th detail. The count is now complete. What has accumulated across these 100 details is not a story in any emotional sense. It is a description, incomplete, inevitably simplified, but grounded in published scientific data of the physical and chemical behavior of matter on and beneath Earth's surface, across timescales ranging from nanoseconds to hundreds of millions of years. This description is not exhaustive. No description of a system this complex could be. Current scientific models carry uncertainty at every scale, in the precise composition of the lower mantle, in the detailed mechanics of dislocation creep at high pressure and temperature, in the exact rate of stalactite growth in any particular cave system, in the role of minor elements in the long-term behavior of hydrothermal fluids. These uncertainties are not failures of scientific method. They are the normal condition of investigating a system not fully accessible to direct measurement, expressed in the language of experimental science. According to current scientific understanding, the crustal and mantle minerals of Earth, dissolving, reprecipitating, transforming under pressure, being carried to depth and returning to the surface, have been cycling without interruption for approximately 4 billion years. The quartz in a beach sand grain today may contain silicon and oxygen atoms that have passed through several generations of minerals, formed in an igneous rock, dissolved by a hydrothermal fluid, reprecipitated in a vein, eroded from that vein, transported by a river, deposited in a sedimentary basin, buried, recrystallized under diagenetic conditions, uplifted and eroded again before arriving at a beach in its current position. Every one of those transitions involved the breaking and reforming of silicon-oxygen bonds. The atoms themselves were never altered. The bonds and structural context changed. The atoms persisted. The gold atoms sitting in a placer deposit in a river gravel may have passed through fewer transitions, perhaps only 1 or 2 hydrothermal episodes since the initial concentration in the original deep magmatic source. Or they may have passed through many erosion and redeposition events over several 100 million years. In either case, the gold atoms are chemically identical to what they were when they were first incorporated into the original magmatic rock. No oxidation, no ionic transport, no structural transformation. The same atomic configuration, protected across geological time by the same relativistic electron structure. This persistence, chemical, structural, atomic, is the quietly running, undramatic theme that extends through the whole of this narration. It is not a theme that calls for any particular response. It is simply a description of what matter does when its thermodynamic stability is high and the environment does not supply sufficient energy to drive it out of that stability. The video is almost over now. The geological processes described will continue at their own pace. The mantle will convect. Water will continue moving through fractured limestone at centimeters per year. Diamond will continue growing in the mantle at fractions of a millimeter per million years. Gold will continue resting in sediment, unchanged, asking nothing. If any single detail from these 100 stays with you, the hydrogen bond network of water, the contracted 6s orbital of gold, the phonon scattering within the atomic voids of granite, that is more than enough. And if nothing in particular remains, that is entirely normal. The information was offered without condition or expectation. If anything from the video left you curious, raised a question, or gave you something to think about, feel free to share it in the comments below. If this is the kind of thing that helps you rest, a like or a subscribe means someone else might find it too. Thank you so much for joining us. Good night. Take care.